So if you have two input variables, P and Q, and a binary output variable or a probability output variable, Y, we use the same logistic function, 1 over 1 plus e power minus z, except now z is now could be a function of your input variables, right? So we use the same logistic function, but you make z, this value, the logistic variable, a function of these two input variables. And if you have even more input variables, you just make this a more complicated, or uh, a function of all the input variables, perhaps a linear function of all the input variables. Okay. The logistic loss function, or the log loss function, is computed in the same way for each data point, P1, Q1, Y1, P2, Q2, Y2, etc. We would compute H of all the inputs, which is computed as 1 over 1 plus e power minus z, where z itself is defined by some expression of all the inputs. For instance, if you have 2D data, 2D data, just to use the same motivating example, which has to do with material failure, you could have stresses, principal stresses, let's say, or stresses in some directions, sigma x and sigma y, and what we would have potentially is data that looks like this, where within a particular region containing sigma x and sigma y, the material will not fail, and outside some region containing sigma and sigma y, the material may fail. So you can have data that looks like this. Or as we just saw in MATLAB, if you want to think of plotting this on the x-axis, this on the y-axis, and y, whether it failed or not, namely 0 or 1 on the z-axis, then basically the function will be equal to 0 here and then 1 outside. Okay, so it'll look like an inverted hat, 0 and then 1 everywhere else. Okay, 0 in a little elliptical region and then 1 elsewhere. Or we might have in other situations data that looks like this, where the output is 0 in some region, input is 0 some other region. This would be called linearly separable, and this would be called not linearly separable, I guess. Okay, and for these things, now the goal is to find B0, B1, and B2 for something like this. For something like this, because you're trying to essentially approximate an elliptical region, we would have a quadratic expression for all these inputs, in terms of all these inputs. So that's a difference, I guess. Depending on the kind of decision boundary that you have either a linear function for z, or a quadratic function for z, a cubic function for z, or maybe something completely different. Okay, there are other ways of approximating nonlinear functions, and maybe you can use all that. Okay, so and then I want to reintroduce this notion of a decision boundary, which is the boundary that separates 0 values of y and 1 values of y, or at least as best estimated by a regression that looks like this. There can also be overlap, right? There can be overlap between these two regions, in which case we'll try to do the best possible job. If there is no overlap, the logistic function will rise steeply. If there is overlap, the logistic function will rise more gradually, and we'll try to find a compromise in some manner. Okay. So the decision boundary in terms of the inputs is generally where z, this variable z, is equal to 0. That corresponds to g equal to 0.5. In other words, a predicted probability of 0.5 for being 0 or 1. So if we take that as the cutoff for saying y equals 1 or y equals 0, z equals 0 is the decision boundary. So z equals 0, or b0 plus b1 x plus b2 sigma x plus b2 sigma y, is basically a straight line in the sigma x, sigma y plane. When you set this equal to 0, that's an equation of a straight line. When you set this equal to 0, that can be an equation of an ellipse, a circle, a pair of hyperbolas, a pair of straight lines, and so on. Okay, so this single equation can actually accommodate all those things. So, and in all these examples, the goal is to find these unknown coefficients. Okay, so just to recap, we are basically implicitly saying that the sort of separation in the prediction for 1 versus 0 is when the predicted probability G is 0.5, which corresponds to Z equals 0, and we are saying basically that Z greater than 1 corresponds to Y equals 1, Z less than 0. Z greater than 0 is Y less equal to 1, Z less than 0 is Y equal to 0. Okay. Okay, so sometimes this procedure of essentially using nonlinear terms here, sigma square, sigma x, sigma y, or cubic, you can imagine other nonlinear terms, is sometimes called a kernel trick in machine learning. So that's something else. And then this is something that we already looked at in the MATLAB version. If you have data that looks like this, where things are one class within a region, things are another class within a region, you can visualize that in this manner with different color markers, or you can visualize it like this, where it's equal to 1 here and 0 here. And then what we are trying to do is essentially approximate, try to find the function h of sigma x, sigma y, which is equal to g of z, that tries to approximate this in a nice manner. Okay. Okay, so let's stop there for this video.